Okay, it's recording now. So, welcome to the third lecture of CE305 Languages and Compiler, or I also like to call this module as the module which teaches you how to build your own compiler. Today, we will be going into details about lexical analysis. Now, before we move into lexical analysis, throughout the lab session and previous lectures as well, we have covered this topic in brief. So who can tell me that what is the purpose of lexical analysis? Can you put that in the chat? Anyone? Any take? What does the lexical analysis do? Split into tokens. Yes. It converts the source. So Matthew says it converts the source into lexical tokens to parse into a tree. Well, to parse into a tree, the parsing comes in the parsing analysis side. But the job of the lexical analysis is technically to create tokens. So Andre, Matthew, both of you are correct. Now, during the lab, we used Antler. Now, in the Antler, what is the process? What is the name of the process that does lexical analysis? We have covered this in the lab. So who can tell me the name of the process? Yes, Matthew, you are correct. Lexer. Perfect. Okay, so moving on with today's lecture. Lexical analysis is technically a type of translation that identifies tokens in the input. Here by input, we mean the original program based on the language that you have written. Now, it takes a step that makes it easier to implement the subsequent parser. So it identifies the tokens in the input, and then it takes a step to make it easier for the parsing analysis to happen. The appropriate patterns for tokens are typically specified using regular expression. Now, before we go into the detail, can someone quickly say what is regular expression? You can write that in the chat. So, Olalekin, am I pronouncing it correctly though? Olalekin? Sorry if I'm butchering your name, please pardon me. So Olalekin mentions that regular expressions are used to match string patterns. Yes, Matthew mentions a pattern that can be searched for in some text. Both of you are completely correct. So regular expression is basically a way or method to search for patterns in strings. Now, in lexical analysis, there are a few issues that is concerning. First of all is the ambiguity. The ambiguity, which we will cover later, it can be related to the context itself. So when tokens are generated, there could be ambiguity that whether a token is complete or it is part of a larger token. In that way, if we do come up with ambiguity during lexical analysis, we need a technique called look ahead to resolve that. Don't worry if you do not understand this completely, because later I will give you example to like related to this as well. So we will be covering this in the lecture. Now, let's take an example of an input program. If you have this input program, where we are doing if I is equal j, then assign 0 to x, or else you assign 1 to x. So this program, the input program, can be thought as just a sequence of character which could be represented like this. So /t for like tab, if, and then I equal j, followed by /n, which is a new line, /t, which is tab, again /t, which is another tab. So for double tabs, then x equals 0, semicolon, and the comment, and so on. So as you can see, so the input program is in 4 lines, but this can be represented as sequence of character as the way shown here. Now, this needs to be partitioned into substrings corresponding to the token of the specified language. Before we move on, we have a couple of chats. So do you need look ahead in interpreters? Yes, interpreters can have look ahead for the line of program that it is executing. So it would also depend on the implementation of the interpreter itself. Depending on language, that may vary, but interpreter also do use look ahead as well. Matthew asked, probably depends on the language, such as interpreter probably processes the entire statement before running it. Yes, Matthew is absolutely correct. So depending on the language for which the interpreter is built, it would depend that look ahead is implemented or not. But look aheads are generally utilized even to understand what's the token for the line of code that interpreter is interpreting. Now, let's look into tokens. So a token consists of a syntactic category plus semantic information conveyed by the underlying string. Tokens convey the role of a given string in a language. Then, after the tokens are generated, parsing operates on syntactic categories rather than directly on words. For example, we can have Joe went to the store or Harry went to the beach. These are example of sentence in English language. They have the same grammatical structure, which means they are part of the same language, which is English. Here, each token would be Joe went to the store. And here, based on the token, the parser relies on token identifiers, and identifier here is treated differently to keyword or white spaces. Now, let's look into tokens in terms of program. In general, tokens in program, they identify the words and their lexical category. When this happens, it is called the lexical analysis. For programming, we tokenize by throwing away formatting and comments, and then identify where a token starts and ends, and assign the appropriate token identifiers. These token identifiers correspond to syntactic categories plus the semantic information of the token. For programs, tokens will correspond to the programming language's notion of a category, such as identifier, integer, keyword, white spaces, and so on. Typically, these will have a compact internal representation based on the platform it is being executed. For programmers, semantic information might correspond to the text of an identifier or numeral or some representation of these values. So to illustrate, a programming language could use tokens defined as follows, such as if we have identifier that can, the identifiers can be strings of letters or digits starting with a letter. You can also have integer, which is a non-empty string of digits. You can also have keywords, which are the specific strings used to express control structure and declarations. For example, if, then, else, begin, end, these are all keywords. White spaces are non-empty sequences of blanks or new lines and tabs. And then you also have comment as well. So some punctuation symbols need to be tokenized as well. We might consider them to be something like keywords. They may be represented by tokens of the same form, such as, let's say, if you have the string like left bracket, right bracket, or bracket open, bracket close, they can be represented as tokens as left bracket and right bracket. Or they can also be represented as distinct token using, let's say, words such as L bracket and R bracket, which means the same. The output of lexical analysis will be a stream of tokens, some of which will include semantic information, such as the value of the identifier itself. Let's take an example of tokenization here, right? The same input program that we saw earlier, if I equal j, then assign 0 to x, then you have a comment as well. Else, you assign 1 to x. Now, this can be tokenized as follows. So you have if, then you have L par. L par here represents the left bracket. You have ID, which is the it's the identifier for the variable I. Then you have equals, you have IDJ for the identifier for the variable j. You have rpar, which is the right bracket, and then so on. Now, keep in mind, this is the tokens that will be created for this input program, especially in Antler. So depending on the different tool that you use to generate the tokens, sometimes the identifier could also vary as well. So this one is an example of creation of tokens in the Antler. Now, as I've already mentioned, that an implementation of lexical analysis should recognize substrings corresponding to tokens. It should also return the value of the lexem or the substring and its corresponding tokens. Now, lexem in its essence could be thought as the substring or word that builds up the sentence for the language. Now, the implementation of lexical analysis should also have the content that is not relevant to parsing, such as comments and white spaces, and these should be discarded. Now, as I've already mentioned earlier, that one of the key issues that happens during lexical analysis is ambiguity. For example, if you have if you have the if keyword, then is the if like whether Is it an identifier I and F, or is it part of the control statement? So when lexical analysis happen or tokenization happen, this type of example, like the program can run through, which forms an issue, because the program, if it finds the character I and F, it doesn't know yet that whether it's a control statement or whether it's the identifier or the variable I and F. Now, we might assume that we solve the problem by considering certain characters, such as you can have white spaces and punctuation, as this would indicate the token boundaries. Now, unfortunately, in general, we cannot rely on specific symbols in the input stream to identify token boundaries. For example, in Fortran, spaces are allowed anywhere for historic reasons, because that's how Fortran was designed initially. Another example, that in C++, you have the template something like foo less than bar greater than. You also have in C++ that if you have the stream syntax such as cin greater than var, this means you're storing the value in the var variable, right? So here you can see how greater than and less than are used in different example of the same C++ language. You can also have nested templates where you can write something like this, foo bar and a bash within the nested symbols of less than and greater than. Now, if tokenization is done in C++, you can see that the program that is actually doing lexical analysis here, it might be confused, because there is a potential conflict in assigning the appropriate token for whether it's a greater than operation, or whether it's part of the syntax, which is greater than and less than and greater than. So in this case, ambiguity happens, and we have to resolve it in some way. Now, we have someone post something in the chat. Is designing, Michael asks, is designing your language to ignore white space just a design choice, or does it have an effect in speed and memory? It usually doesn't have too much effect on speed and memory. Of course, you can completely you can write a language where you do not think about white spaces at all. But usually when tokenization happens, which takes care or discards all the white spaces, usually that process happens in nanosecond in most of the computing system in today's age. So we do not have to worry about performance in that sense. And we also do not have to worry about memory in this sense, because although depending on the programming language that you are designing, when tokenization happens, since you as part of the rule, you're already mentioning that just avoid white spaces. So in the lexical analysis stage, the lexer automatically just gets rid of any white spaces and determines which is a token or not accordingly. Yes, it does affect speed, but very minimal, because it happens in nanosecond, but usually you do not have to worry about it. Memory, not that much so, because Lexer takes care of it. So you do not have to worry about memory. Now, I can show you a quick example on this one. So if you can remember our expression grammar that we did in lab 1 and also yesterday's lab 2 as well. So here you can see we have specifically mention that ignore the white spaces, which is WS, here we are mentioning that just get rid of the space and the tab, you just skip it. So based on this rule, the Lexer will automatically skip that, and it does not have any effect on the memory, but it has like nanosecond difference in the speed, execution speed. But again, nanosecond is technically nothing when it compares to the whole execution of the compilation process. I hope that makes sense. Now let's go back to the lecture. Okay, we have a question. Let's. So space R, forget, it's for carriage return, if I can remember it correctly. So now that we have understood what is ambiguity that can happen as part of lexical analysis, let's look at the solution to kind of resolve this. So in some cases, the only solution to resolve ambiguity is to use look-ahead algorithms to ensure we do not misclassify a substring. For example, a lexical analyzer for C or Java must read ahead after it sees the character greater than. So if the next character is equal, then greater, it could be like the program understand that greater than is part of the sequence which is greater than equal. If the next character through look ahead is not a equal sign, then greater than, instead it forms the greater than operator only. Usually like one character read ahead is like what it takes to kind of resolve the ambiguity issue. So a simple solution is to use a variable to hold the next input character in your look ahead algorithm to resolve this. A lexical analyzer can read ahead one character while it collects digits for numbers or characters for the identifiers. So it read past 1 to distinguish between 1 and 10. So what is meant by this? Let's say if you have a one-digit number, or if you have more than one-digit number, then it uses that one character to understand what is the next character that is coming in, whether it's a number or a white space or like symbol. And based on this, the lexical analyzer can use the look ahead algorithm to get past ambiguity issues. The lexical analyzer reads ahead only when it has to do that. For example, like if you have an operator like the star, which is the multiplication symbol, then it knows that it doesn't have to worry about this star being the token or not. Star is always just a token on its own. So in this case, lexical analyzer do not have to do a look ahead. And as I've mentioned, if it finds a symbol like star, it automatically understands that this is a token. So just to recap what we have just discussed as part of the lexical analyzer, that it identify the relevant lexems or the substrings and their corresponding tokens in the input program. As we typically scan the input from left to right, we may need look ahead to resolve local ambiguity issues. We still need a way to describe the lexems that correspond to a given token, and an algorithm for using those descriptions to match the lexem. And in this case, you might need look ahead as well. Now we have in someone asked in the chat. So lexers are traditionally greedy. Again, I wouldn't say traditionally. Uh, it would completely depend on the implementation. Now you have to understand what we are discussing right now is the essence. But the implementation can vary, if that makes sense, Matthew. So whatever we discussed so far is, let's say, the theory behind lexical analysis and what kind of challenges or issues that might happen. But that being said, we also have solution for that. So this is just like one of the example of, in case a lexical analysis, if we do have an issue which is ambiguity happening, then you can resolve it using the solution called look ahead. But that does not usually makes Lexer greedy instead. It's just the theory behind it and one of the possible issues of lexical analysis in implementation wise. Now, let's look into regular expressions and grammar. Now, as I have already mentioned that in lexical analysis, while forming the tokens, regular expression plays an important part in it. So we need to be able to express or define the strings that belong to each token. It turns out that individual words and lexemes of both programming languages and human-like languages can be characterized within a class of regular languages, equivalent in the power of regular expression. As we already know, regular expression is like type of algorithm that helps you to search for something in a sentence. And if a language follows the regular expression, then or set of regular expressions, then it is called a regular language. Now, regular expressions denote formal languages, which are set of strings of the symbol for some alphabets. Regular expressions are easy to understand and allow efficient implementation as well. So the theory of regular expression and the languages they characterize are very useful to understand. Now, in general, if we have a language L, that can be defined as a sequence of symbols drawn from an alphabet, which is denoted by the capital epsilon or big epsilon. But we will be calling it as alphabet for the sake of the lecture right now, sake of understanding. So language over alphabet is just an identified subset of strings drawn from elements of the alphabet itself. In the case of lexical analysis for a compiler, the alphabet consists of characters. It also consists of the sequence or strings, which are the lexemes of the programming language. Now, a given language may be characterized by a grammar G. We can say that the language generated or specified by G is L within brackets G. So here the L within brackets G is the language that is specified by the grammar G. As we shall see later, that grammars and the languages they specify can be seen to fall into different classes corresponding to the computational power needed to parse strings of that language. Tokens fall into the class of so-called regular languages. These can be specified using regular expressions, as I've already mentioned. That is, that regular expression provide a means of specifying the grammar needed to identify the lexemes of a program. Now, let's see that how regular expression as a grammar specifying a language can be used. Let's say if you have the expression R here, denotes the language, which is L within brackets R, over the alphabet, then this, the one of the way we can define it is L within brackets small epsilon, which means here a small epsilon usually denotes empty. So here the language is empty. If C is a character in the alphabet, then the C is part of the alphabet itself, or C belongs to alphabet. And then the language can be defined as L within bracket C, or it can be like said that L is comprised of C itself. If you have like a regular expression in other ways, then you can see like we can form different combination of the regular expression to form the language itself. Now here, one thing that you need to keep in mind, that precedence is like very important in order for regular expression to be defined and the language to be defined based on the regular expression. For example, if you have the multiplication or the star sign, that has the highest precedence. Concatenation is the like next to the highest precedence, which is the star. Union has the lowest precedence. Parentheses also provide grouping, so they also have precedence in this case as well. Now, before we move forward, we have someone ask something in the chat. So Sokainia has asked, when the tokens are created, wouldn't the syntactic parsing process them to generate an IR code? So after the tokens are created, then the syntactic analysis happens, where the parsing comes into play, like the parser comes into play. Parsing happens on the tokens in order to form the parse tree. Now, parse tree itself can be thought as an IR code, or intermediate representation code, or it can be optimized further to create IR code as well. But right now, we are discussing lexical analysis, which is the process of generating tokens itself. Now, she also asked, would the syntactic parsing in this case solve any lexical ambiguity? If yes, why do we need the look-ahead algorithm? Now, again, when syntactic parsing happens, or like parsing analysis happens, here look-ahead is not needed, or ambiguity is not needed, because ambiguity happens when determining something is a token or not, or what is a token. So look ahead is usually implemented as part of the lexer, where any form of ambiguity can be got rid of, and the token is generated eventually. Okay. Now, there are some very common abbreviations that are used as part of regular expression, such as if you have L for the like within the brackets R to the power right bracket, then this actually means that L, the language, forms of R R star. Now, whenever you see the star, it means it's a continuation statement. So R can be followed by R. So that's what it means here. Another abbreviation can be L, forms of R question mark, which means that L can be formed of empty or it can be formed of R. We also have some implementation specific abbreviation as well. So depending on how the regular expression are implemented as part of the tool, you can also have a different type of abbreviation based on that. For example, if you have a character list such as A, B, C, F to M, X, Y, this is an abbreviation for the character list in Java, Perl, or Python programming languages. So as you can see, this shows that as part of the regular expression implementation in a particular language or tool, there are certain abbreviations that you need to be mindful of. Now, you also have character classes, such as you have dot or \d or \s. So in Java, Perl, and Python, \d actually means the double integer. It denotes the double integer. Or if you have \s, it will denote the string. So in Java, Perl, Python, these are the abbreviation used as part of regular expression as well. You can also see that if you have A followed by question mark in as part of regular expression implementation, this actually means it is equivalent to either A or empty string. Excuse me. Now, if you see something as part of a regular expression as A pipe B, here sometimes it can be like expanded to be written as A plus B. Another example is if you have ABCD within second bracket, then this can mean that it's either A or B or C or D. If you have A minus D, here it's actually not minus, it means A till D. So this would mean that it forms A, B, C, D. And if you have A to the power plus, this actually means that A followed by A and star. Now, as I have already mentioned, that if you have a star, that means that it continues with itself. So this will technically mean that A followed by A star here can be followed by A and A star again, and so on. Now, let's take a look at few examples. So if you have the alphabet consisting of A and B, here, if the regular expression is A pipe B, that denotes the language itself, which is A or B. If you have within bracket A pipe B and again within bracket A pipe B, this actually denotes that the language is formed of AA, AB, BA, and BB. Here, the language of all the strings of length 2 over the alphabet. Another regular expression for the same language is, or it can be denoted as AA, pipe AB, pipe BA, pipe BB. Now, as I've already mentioned, A star denotes the language consisting of all string of 0 or more A's itself. So A continues on its own. For example, if you have A star, that would actually mean that the language consists of epsilon, like this is a small epsilon, this means it's empty, or A, or AA, AAA, and so on. If you have A pipe B within bracket star, then this denotes the set of all strings consisting of 0, which is epsilon, or more instances of A or B. That is, it's the string of A's and B's together. For example, Here, if you have a pipe b within bracket to the power star, then it will form of all these, this set with all these string, which is the empty a, b, a, b, ba, and so on. And if you have a pipe a star b, that denotes the language as a, b, AB, AAB, and so on. So here it means that the string A and all the string consisting of 0 or more A's ending in B. Now, C identifiers are technically like a string of letters, digits, and underscore. Here is a regular definition of the language of C identifiers. So if you have letter, that means like letter consists of A, B, C, D, and like till Z and so on. If you have digit, it will consist of 0, 1, and till 9. If you have ID, that means here the regular expression can be denoted as letter within brackets letter or digit star. So this one means that a letter can be either it forms of a character, which is like A, B, and so on, or it can also form of a digit 0 till 9 as well, and it continues. Now, this is the theoretical side. I want to show you an example in the practical side. So here, as you can see, as part of the regular expression, in your grammar, if you can recall in the expression grammar where we had the first one, right? Like what can be expression. So here we are defining expression followed by a new line and star. It means expression can follow a new line, or expression can follow an expression and a new line, and so on. This is also a representation of regular expression used in the grammar for your ANTLR tool. Now, coming back to the lecture. So, few other example, like I would like to give you that if you have unsigned numbers such as integer or floating point, these are technically strings which can be denoted by like 5280 or 0 point or 0 dot 0 1 2 3 4 and so on. So the regular definition is a precise specification for this set of strings. Now, an optional fraction is either a decimal point or dot followed by one or more digits, or it is missing, which means it can be an empty string as well. Whereas an optional exponent, if like there is no empty string or if not missing, is the letter E followed by an optional plus or minus sign, followed by one or more digits, which means that if you like sorry, where is my mouse? Oh, yes. So the number, if it doesn't match, like if you have one dot and then empty, then it does not like match it. So you have to have the number that if you have a dot in the number and it's followed by another digit, then that is valid in this case. So let's recap. We can now use regular expression to define lexems corresponding to individual tokens. We still need to find the algorithm for identifying these lexem in an input string or input program. Ideally, it should be possible to generate such algorithm directly from a collection of regular expressions. So if you can recall from our expression grammar, as I will show you here. So here, these are all like a form of regular expression. And all these regular expression forms a set of rules which is part of the grammar. So in order to understand that what is a token in the input, you have to use set of regular expressions to determine the token. So there are many tools to help you with this. Antler is one of the tools which you are using in practical, like in the labs, to help you form the tokens. Such tools compile the specification into a program that implements the lexical analysis parser. Now, we will be going through some sample problems like in different languages just to see how they work in the practical sense. For example, if we have to define the decimal numbers in C or Java, a regular expression can be defined like this. So 0, like a pipe, or it can be 1 to 9 digit, or it can be 0 to 9 followed by star. If you can recall, star means it's a continuation of that digit and so on. Now, another example is if we have all numerals in, if we consider all numerals in C and Java, then that can be denoted as a regular expression like this. If we consider floating point numerals, then that is denoted by the regular expression like this one, as shown in the slide. Here, keep in mind that \t means the digit, or it means like 0 to 9. Now, identifiers in C or Java can be expressed as regular expression like this one, A to Z and capital A to Z, or it can be followed by small a to Z, capital A to Z, and digits as well, 0 to 9, and then star because it can be continuation as well. And we have commands in C++ and Java which can be used which can be denoted by the regular expression using this form. Now we also have keywords which can be if, then, and else. So as part of regular expression, if you have to form regular expression for keyword, it will be like this: if or like pipe sign, then pipe sign, else. Now here the string can be abbreviated. If you have a string which is string, then that can be abbreviated as like this form in the regular expression. Other things to keep in mind that you can also have white spaces as well, which is like non-empties sequence of blanks, tabs, and new line. And the regular expression for that like white spaces can be expressed like this. For integer, which is the non-empty string of digit, regular expression can be defined like this, where we define each digit and then we say integer is formed of digit followed by digit star, which means an integer can be of many digits, not just one digit, but many. So this is just defining that as in terms of regular expression. Now, based on these examples, it can be clearer and more convenient to decompose the lexem definition itself to generate the tokens. Let's see also the example of identifier. Identifier is the strings of digits or letters starting with a letter. So the regular expression for that can be expressed in this way, where you have letter equals A, B, C to like Z, and like capital letter and small letter. Now remember one thing, that how we put capital letter one first and the small letter next. It's because when it comes to, let's say, English language, a letter, like the sentence, starts with capital letter, right? So remember, I have already mentioned precedence is important. That's why here in the letter, we define the capital letter first and then the small letters. And then the identifier can be defined as regular expression by using letter, within brackets letter, or it can also be followed by digit star. Now, I want to show you a practical example in Antler. So here you, as I have already mentioned, expression followed by new line star. This is a regular expression as well. Whereas another one, in the grammar, you have that expression can be followed by star or division sign followed by expression. So this is a practical example of regular expression as well that I have already mentioned. Now, if you have to use regular expression to define email address, a very simplistic way of doing that is you define the regular expression that you have the epsilon, which consists of letters to the power plus, and also consists of at the rate or dot sign. And then you also define that name consists of letter to the power plus. Here, then, if you have to form regular expression for email address, the simple one would be something like this, where name followed by at the rate sign, name within brackets dot name to the power plus. Now, this is the regular expression form for to define email address. But one issue with this, that it's like inadequate to some sense, because if we use this regular expression, sometime it can also form domains that are illegal or that are not legitimate. Though we can use regular expression to define any string, but we have to keep in mind that sometime it can also like the same regular expression can also validate illegal string as well. And this is an example of that. Now, other example in, okay, we have someone post in the chat. Let's take. Will we have more practice on how to define a regular expression? We would not have, but these are only for like examples. As part of the lab, we have provided some because as part of the lab, we have provided several examples of different grammars. So technically we have, as part of the grammar, we have provided several examples of regular expression, but the best way to learn about regular expression on your own is there is a website on like regular expression. So if you just Google for regular expression, you would be able to find out resources on that. So I just checked the previous final exam, and a huge part of it is about regular expression. Yes, some of the exam do consist of regular expression. Your books also do have chapter on that. So do follow the compiler's book, the Dragon book, in that you do have regular expression, as well as if you follow the Antler book, they have example like how to define grammar. As part of that, they also provide regular expression as well. So you can follow these resources, or I personally also am a big fan of like online resources, because it gives you definitive example of, okay, how to form regular expression of different type of strings. So do use these resources to get more in-depth and better understanding of regular expression. I hope that helps, Kenya. Okay, quickly let me check. Okay, yes. So in Pascal-like numbers, you have signed numbers, which is like with optional fraction part and with optional exponent as well. So if like in Pascal-like language, if you have to define like numbers, then let's see how they can be defined using regular expression. So you define the digit, which is formed of 0 till 9. And digit can be like, again, digit plus, so it can be followed by itself. So because a number can be either single digit or many digits, so this is the regular expression for to define it in that sense. You also define optional signs, which is plus, minus, or epsilon. So this is to define whether the number is signed or not. Not here would be the empty or epsilon. You have optional fraction that can be defined by dot itself, followed by digit, or it can be empty as well. It doesn't have to be optional fraction, but it can be. And this is the expression that you use to define optional fraction. And based on these regular expression that we have defined, you can build up the also the optional expression itself, which is E, like here, followed by the optional sign, followed by the digits. Or because it can be empty as well, that's why we also define the expression in this way. A number here in based on these expression can be defined as optional sign followed by digit followed by optional fraction followed by optional expression. So you can see, to build up a signed number with optional fractional part or optional exponent part in a Pascal-like language, you have to define these expression in order to define the number itself. Now this itself is the whole thing. When you put all these expressions together, this is part of the grammar to define numbers for this particular language. Now, combining token definitions, because as I have already mentioned, or even better, I will show with an example here. So in order to define different type of tokens that your language can support, so in the grammar, or here in the sense of in the grammar file, you have to define different type of regular expression to to confirm the different type of tokens. So all possible tokens can be defined by a single structured regular expression itself. The names of the regular expression defined at the highest level, this then correspond to the token identifiers. For example, if I go back here, the prog is the name of the regular expression, which is defined by the expression new line star. So in summary, what we have learned today is that like regular expressions are useful for defining languages. They are a specification, but not an implementation. So it's more like a blueprint that builds up your language. We need some form or some way of checking whether a string S lies in the language defined by a regular expression R. And that's why we use the regular expressions. So if we mention this, that we need to check whether a string S lies in the language defined by a regular expression are, this means that we need to compute S belongs to L R. So this is the mathematical representation to search whether a string lies within a regular expression for the language or not. So that being said, we reached the end of today's lecture. Next week, we will be going into state machines. So non-deterministic state machine, or non-deterministic automata and deterministic automata, which plays an important role of taking the tokens and building the parse tree. Now, before we conclude, I also wanted to show you an example. So here, these are some of the example of Lexical rules that are used in our Antler tool for the lab. Now, do not worry, I will actually be like, do not worry of taking down notes or taking a screenshot right now, because I will post this as an example in the chat forum later today for you to be able to use it in case you want to use it as part of your language that you need to do as part of your assignment. So let me stop sharing. Is there any question that you would like to ask? Any question? Anyone? I thought, so Curtis asked, I thought you would show us more explanation on what goes on in the visitor. What do you mean by that? Because again, we discussed the listener and visitor in last week's class. We have also provided several examples in the labs. But in case you want to get some more examples of visitor, I can definitely like show you that in next class. I can prepare a separate lecture specifically for visitor, and I can show you with example some of the things. Although I think it would be better if I do it in next lab on Monday. So during the lab, I can show you examples of visitors. But again, if you want to go behind the theory of visitors, uh, do look at my lecture from the last week, because that's where we explain the like theory behind it. Once again, next week, Monday, during the lab, I will bring some example in the lab for us to kind of go through it. So Andre mentions, okay, practice need. So Kanya mentioned, I agree with Andre, practice needed to get familiar with regular expression. Yes. See, one of the key things is we discuss about the theory here, but now when you go into developing your own grammar for the language that you want to build, again, the grammar itself forms of different regular expression, as I have already mentioned, right? Now, regular expression is technically based on practice. There's no more explanation that I can give, because it actually forms, like regular expression usually follows a standardization or standardized format. So you have to go through the book materials and online material to just to make yourself familiar with different form of regular expression, so that you can start building your grammar on your own. So absolutely, practice is the next thing that is like left for you to do. Okay, Curtis mentions, yeah, that's fine. I just wanted to get more explanation on the solution for this week's lab. But we can do that next week. So again, This week's lab, one thing I think we haven't, like I haven't, like I have mentioned, but it might not be clear to everyone. The only reason why I have made all the labs available from the beginning is that during the lab, you might have noticed that actually all the code are provided to you in different ways with different example. Now, the best way to learn how to program something is to actually experiment with the provided uh, examples itself, especially when it comes to developing your own compiler or languages. Because Antler on its own also follows a specific syntax of writing grammar. And based on the grammar, you create tokens and also the parse tree, or you can extend that to create other form of output or intermediate representation code. But these, when you are using Antler, they specifically follow some form of format, which comes with more practice. If you specifically have question on something that you are not able to understand, please let me know so that I can use that as an example to explain further. So Curtis, if you can give me specific example that which like part of the exemplar code you would like to get better understanding, then I can specifically give you explanation on that, if that makes sense. So Curtis, if it is part of the, you mentioned that I will send an email. I think uh, it might be even better that if you think it will help other people as well, uh, ask the question in the chat forum. So I can also answer in the chat forum. And in case if someone else like your peer in the course also find it useful or they have the same question, then the same answer, like it would answer or clarify their query as well. Okay, let me stop the recording here today.